Hi guys, welcome back to the second part of electrochemistry where I'm going to deal with the electrolysis. First part is already up where I dealt with electrochemical cells, and in this I'll be dealing with the topic electrolysis. I start with Faraday's laws, a quick look into Faraday's laws. Faraday's laws were proposed by Michael Faraday, and he proposed first law of electrolysis and second law. First law of electrolysis suggests amount of substance that is deposited or liberated at any electrode is proportional to the quantity of electricity passing through the electrolytic solution. So as questions, this is an important question. Define Faraday's first law. And mathematically, if we look at this law mathematically, it says M is directly proportional to Q. That is, mass is directly proportional to quantity of electricity passing through the solution. M is equal to ZQ, where Z is the electrochemical equivalent. Z is the electrochemical equivalent, and Q is equal to IT, where I is current and T is time in seconds. Q is current in ampere. So M is equal to ZIT, or M is equal to EIT by 96500. Remember, Z, the electrochemical equivalent, is E upon F, where F is F1 Faraday is the charge carried by Avogadro number of electrons, which is going to be equal to charge on one electron into Avogadro number. When calculated, approximately rounded off comes out to be this. So one of the questions which can be asked is, what is the unit of Faraday's constant? What is the unit of Faraday's constant? So if this question is asked, the unit of Faraday's constant is Coulomb per mole. The unit of Faraday's constant is Coulomb per mole. Right? Now, Z is the electrochemical equivalent and E is called the chemical equivalent. So one of the questions possible is difference between electrochemical equivalent, that is Z, and chemical equivalent, that is E. So remember, electrochemical equivalent Z is the amount of substance deposited on passage of 1 Coulomb charge, and chemical equivalent E is the amount of substance deposited on passage of 1 Faraday charge. So how can we derive one from another? 96500 Coulomb deposits a quantity equal to 1 gram equivalent, or equivalent weight in gram equal quantity. So 1 Coulomb is going to deposit the quantity equal to equivalent weight upon 96500, and this is E upon F, and we call this quantity E upon F to be equal to Z. So the electrochemical equivalent Z is equal to chemical equivalent E upon Faraday. So unit of Faraday's constant is Coulomb per mole. These are important definitions. Electrochemical equivalent by 1 Coulomb charge, and chemical equivalent deposited by 1 Faraday charge. Moving on to the next point. Please learn all this. Any of these questions are possible for your exam. Second law of electrolysis has been derived from first law itself. It says if the same quantity of electricity is passed through different electrolytic solutions, then the amount of substance deposited or liberated at electrodes is proportional to their chemical equivalent weights, right? So we have 3 solutions in series, connected in series, and if we apply the first law of electrolysis to each one, so W1 is going to be equal to E1 into Q, where Q is the quantity of electricity passed through the solution. W2 is going to be equal to E2 into Q. This also upon F, right? Or I can say W1 is equal to Z1 into Q. W2 is equal to Z2 into Q. Similarly, W3 is going to be E3, that is equivalent weight upon F into Q, or it is equal to Z3 into Q. Fine. So Now, why Q in each of the cases? Because we are passing the same quantity of electricity through the three solutions. Now, W1 upon W2 is going to be equal to E1 upon E2. If we take the ratio, Q and F will cancel off. We are going to be left with W1 upon W2 is equal to E1 upon E2. Similarly, I can take W2 upon W3 is equal to E2 upon E3. So how can I conclude this law? The amount of a substance deposited is directly proportional to its equivalent weight. So this is what the second law says. So basically this law has been derived using the first law. So important questions: definition of first law, definition of second law, difference between chemical equivalent and electrochemical equivalent, or what is either of these, and what is the unit of Faraday's constant. So this is the mathematical relation that we derived from second law of electrolysis. The weight of substance deposited is in proportion to their equivalent weights. Coming to a question, a solution of copper sulfate is electrolyzed for 10 minutes. For 10 minutes, that means time T is equal to 10 minutes, which we will convert 2 seconds by multiplying with 60. We get time is 600 seconds with a current of 1.5 ampere. The question asked is, what is the mass of copper deposited? So what formula are we going to use? The formula we are going to apply here is W is equal to ZIT, where Z is E upon F into IT. So we always know equivalent weight. What is equivalent weight? Equivalent weight is basically molecular weight upon the N factor. And what is N factor here? N factor is based on the total positive or total negative charge. So molecular weight by 2 is going to be equivalent weight. Equivalent weight is molecular weight upon 2 into current is 1.5, time is 600 seconds. Put the molecular weight, multiply and solve. So let us observe. Valency is 2. N factor is 2 because 2 electrons are being exchanged. So equivalent weight of copper ion is 63.5 upon 2. This is the atomic weight of copper. This is the N factor. Why N factor is 2? Because 2 electrons are being exchanged during this process. So the formula becomes this. I into T, 900 coulombs. So we have E upon F. This is atomic weight upon N factor. This much is E, this is F, and this is Q. So when you solve, you get the answer as 0.29 gram. Two electrolytic solutions, 0.2 molar ferrous sulfate and 0.2 molar ferric chloride. Ferrous sulfate and ferric chloride are subjected to electrolysis. The ratio of weight of iron deposited in the two cells under the same time is how much? So remember, the ratio of weight of iron deposited is in ratio of their equivalent weights. So how do we work on this? Weight of ferrous from ferrous sulfate upon weight of ferric from ferric chloride is going to be in ratio of their equivalent weights. Why? According to second law of electrolysis, W1 upon W2 is E1 upon E2. So what is E? E is 56 by 2 for ferrous ion and 56 by 3 for ferric ion. Why? Because it's atomic weight upon the N factor, which is equal to the charge. So simply take a ratio. We are going to get our answer as 3 by 2. Equivalent weight of ferrous is 56 by 2. Equivalent weight of ferric is 56 by 3. This cancels off. We are left with the ratio 3 by 2. Moving on to the next. Number of coulombs is required to deposit 5.4 gram of aluminium when the given electrode reaction is represented. So how can you go about this? You know, either you think it like this: aluminium plus 3 electrons to give Al. 27 gram of aluminium is deposited by 3 Faraday charge. This is 1 mole of aluminium, which means 27 gram of aluminium ion is going to be deposited by 3 moles of electrons, and 3 moles of electrons means 3 Faraday charge. So 5.4 gram will be deposited by how much? 3 upon 27 into 5.4. So solve this, you're going to get your answer in Faraday, and multiply this with 96500 coulomb, you get your answer in coulomb. Okay, so if we look at the solution, we're going to observe the answer to be 57900 coulomb. And how to proceed? Another way that we can relate is calculate the equivalent weight. What is equivalent weight? Equivalent weight is equal to atomic weight upon n factor. Why n factor is 3? Because aluminium is a 3 plus ion. 9 gram, which means 1 Faraday charge is going to deposit 9 gram. 1 Faraday charge will always deposit gram equivalent weight of any substance. So 1 Faraday is going to deposit 9 gram. 9 gram from 1 Faraday to 5.4 gram will be deposited by 1 upon 9 into 5.4. This answer is in Faraday. If you want in coulombs, so 1 upon 9 into 5.4 into 96500 coulomb. So this gives you your answer. Very important type of questions. Moving on to the next. How much charge is required for the following reduction? For this, what are you going to calculate? For permanganate ion to Mn2 plus, how much charge is required? So you are going to calculate the oxidation state of manganese. How do we do that? Let us assume this to be X. X minus 8 is equal to minus 1. Why? Because each O is O2 negative. So O2 negative into 4 is minus 8, and this is the total charge. Minus 1 is the total charge. So X comes out to be plus 7. This is plus 7. Plus 7 is going to plus 2. That means there's reduction using 5 electrons. Hence, to convert 1 mole of permanganate ion to manganese ion, we would need 5 mole of electrons or 5 Faraday charge. In case you need to give your answer in coulomb, 5 into 96500 coulomb of charge. So the answer to this one is going to be either 5 Faraday charge or 5 into 96500 coulomb charge. Similarly, how much charge is required to convert 2 moles of water to oxygen? So 2 moles of water to oxygen. This is minus 2. This is 0 per mole water. How many electrons are needed? Per mole of water, 2 Faraday charge is required. Why? Because each mole of water has 1 O, and that 1 O is undergoing a change from minus 2 to 0. 2 moles of water will have 2 oxygens. So for 2 moles of water, 4 Faraday charge will be required. So 2 moles of water to oxygen, the amount of charge required is 4 Faraday, or 4 into 96500 coulomb. Similarly, if the question asked was 1 mole of potassium dichromate or 1 mole of dichromate ions to chromium 3 plus ions. So how are we going to work on this? Dichromate Cr2O72 negative to Cr3 plus. Now each chromium here is plus 6. Each is plus 6. Here each chromium is 3 plus. So per chromium, the change in oxidation state is by 3 units. Plus 6 to plus 3. So per mole of dichromate ions, change in oxidation state, or let us say instead of mole, let me first take per unit of dichromate ion, change in oxidation state is going to be by 6 units. Why 6 units? Each dichromate has 2 chromium. Each chromium is showing a change from plus 6 to plus 3. So per mole or per single unit of dichromate, the change in oxidation state is going to be by 6 units. Okay. So per mole of dichromate ion, what will be needed? 6 Faraday charge, means 6 moles of electrons, 6 Faraday charge is required. Or what answer will we quote if we are asked in coulombs? 6 into 96500 coulomb. So the common mistake that you children tend to make is not considering this 2. So remember, oxidation state is plus 6 for each chromium. Since per mole of dichromate 2 chromiums are involved, so the net change is going to be by 6 units. Per chromium 3, for 2 chromiums per mole of dichromate 6. Hence, for 1 mole of dichromate ion, 2 chromium ion, for 1 mole of dichromate ion, 2 chromium ion, the total charge in coulomb required is going to be 6 into 96500 coulomb. Very important type of questions. The next is 2 electrolytic cells containing silver nitrate solution and copper sulfate solution connected in series. So that means we're going to use second law. A steady current of 2.5 amperes was passed through them till this much of silver was deposited. How long did the current flow and what weight of copper will be deposited? So how long did the current flow? For this part, we're going to use the first law. How? W is equal to ZIT, where Z is E upon FIT. So you know W, 1.078 is W for silver. Equivalent weight of silver is its atomic weight by N factor. F is 96500 and amperes 2.5. Time in seconds will be calculated from here. Okay. Second, it says how long did the current, what weight of copper will be deposited. For that, W1, let us say this is W silver upon W copper, is E silver upon E copper. What is W silver? 1.078 upon W copper is what we need to calculate. E silver is 108 upon 1 and E copper is going to be its mass upon its N factor. Why N factor is 2? Because copper sulfate formula is this, with copper being a 2 plus ion. So solve this and you will get the weight of copper deposited. This we have used for the first part. We've used first law of electrolysis. W is equal to ZIT. And for this we have used the second law of electrolysis. This is using second law. Okay, so all these are the probable questions from laws of electrolysis. Laws of electrolysis. So you will finally get the answer for time as 6 minutes 26 seconds when you solve this. Now this is another very important question type. Silver is electro deposited on a metallic vessel of surface area this much by passing a current of 0.2 ampere for 3 hours. Calculate the thickness of silver deposited given the density of silver is this much. Now, how are we going to solve this question? This is one of the important questions, very common questions. So how do we go about? See, first quantity of electricity passed. It says silver is deposited on a metallic vessel of surface area this much by passing a current of 0.2. I is 0.2 ampere. T is 3 hours, means 3 into 3600 seconds. Right? W is equal to ZIT. Right? This is going to give us W. So once you calculate W, you know the amount, the mass deposited, you're going to get this answer. Then, so once you know density is equal to weight upon volume, weight is equal to this, you need volume. So volume is going to be what? Weight upon density. Fine. So this is 10.47. This. When you're going to substitute, you're going to get volume equal to this. Now you know volume is equal to area into thickness. Area into thickness. So the thickness deposited is going to be volume upon area. Substitute the values and you get your answer. Be careful about the units. The correct usage of units throughout. We are talking about electrolytic cells and electrolysis. So electrolytic cell first the uses. This is an electrochemical process, one of the greatest important aspects in the laboratory in the chemical industry, used commonly for extraction of metals from ores. Electrolysis. For an electrolytic cell, we have an anode, a cathode, anode where oxidation occurs, and the component having higher oxidation potential gets oxidized easily. Cathode is the electrode, negative electrode where reduction occurs, and the substance having higher reduction potential would get reduced easily. And DC is used as an external source of voltage, direct current. Now we have two kinds of electrodes. One are the non-attackable or inert electrodes. These are inert or non-attackable electrodes, means they do not participate or compete for the reaction. Generally, the less reactive metals like platinum or gold act as non-attackable electrodes. Okay, and these can act only as source or sinks of electrons. And the second kind of electrodes are attackable electrodes. Attackable electrodes are those which are reactive. These are reactive electrodes. They participate in the electrode reaction. That means they can compete for undergoing the reaction with other components. Now for aqueous solutions of salts, how do we decide the product? If the metal is more reactive than hydrogen, then hydrogen gas gets liberated at cathode. For cathode, there has to be reduction. If it's a metal ion, it undergoes reduction like this. If it is hydrogen ion, it undergoes reduction like this. So out of a metal ion, and hydrogen ion, which gets liberated depends upon which has a higher standard reduction potential. So if the metal is less reactive, like silver, copper, or has a lower oxidation potential or a higher reduction potential, then it gets preferentially deposited at cathode. Metals with. Now, in general, rules for ionic solutions for deposition are: anions are halogens, that is chloride, bromide, and iodide. In comparison to water getting oxidized, the halide ion gets oxidized. But if we have any oxo anions like sulfate, nitrate, carbonate, fluoride, etc., then water gets oxidized and we get oxygen as the product. Now, how to decide the product? So, halide ions and water comparison, it is halide ions which are preferentially oxidized, but for oxo anions and water comparison, it is water that gets preferentially oxidized. Now, while writing down oxidation of water, how can we show? Either we can show oxidation of OH negative ions. OH negative ion losing one electron to form OH. This is the primary change. And this OH further converts to oxygen plus water. This is the secondary change. Okay. Or we can write this reaction. If I just cancel off, multiply this equation with 4, cancel off this and this, what overall reaction do we get? On adding the two equations, we get the reaction 4OH negative ion minus 4 electrons to give 2 water plus oxygen, or these 4 electrons from here can be taken to the other side and written like this. So this is the reaction. 4 OH negative ions undergoing oxidation to form 2 water, oxygen and 4 electrons. And which element is getting oxidized? O is getting oxidized from -2 to 0. So O gets liberated as a gas. This is how we write the oxidation of water. Oxidation of OH negative ion. OH negative ion loses electron and then 4OH forms water and oxygen, where the oxidation state -2 is changing to 0. And to balance, this is 2 water. Right? If I have to find out the overall equation, this is called as the primary change. This is called the secondary change. And in order to get an overall reaction, I multiply this with 4. So that 4OH and 4OH, the intermediates get cancelled. And the overall equation becomes 4OH negative to give 2 water plus oxygen plus 4 electrons. Or if I put 4H plus ions both sides, then 4OH negative 4H positive will become 4 water. This will become 2 water plus O2 plus 4 electron plus 4H plus. So 2 water here go. We get another form of the equation, 2 water to give 4H plus 4 electrons plus oxygen. So this can be expressed as oxidation of water, where -2 of O is converting to 0. Or I can express it as oxidation of OH negative ion. Both actually mean the same. So similarly, when we are talking of at cathode, at cathode reduction takes place. So standard reduction potential of water is greater than standard reduction potential of metals of group 1, 2 and 13, such as sodium, potassium, calcium, aluminium, etc. So in comparison of these, since standard reduction potential of water or H plus ions is more than that of these metals, so preferentially H plus gets reduced to form hydrogen gas. How can we show the equation for reduction of H plus? Either you show it as H plus 2 electrons to give hydrogen gas, or if you want to show reduction of water, so simply add 2 OH negative this side and 2 OH negative this side. So 2H plus 2 OH negative will make 2 water. These 2 electrons as such, and this side we have hydrogen gas plus OH negative ion. So both these equations basically stand for the same. Either write it in this form or write it in this form. Okay, here I have shown 2H plus 2 OH negative and rest of the things same. Basically we have added on this equation, I've added 2 OH negative both sides, and then H plus OH negative become 2 water. So this is another form of the equation. This basically represents reduction of water or reduction of H plus liberating hydrogen gas. And this was oxidation of OH negative or oxidation of water, liberating oxygen gas. Okay. Now, in case we have less reactive metals, that means metals which have higher standard reduction potential than that of water, we can use a memory aid called CHAPA for this. CHAPA, where C stands for copper, H for mercury, A for silver, P for platinum, and A for gold. So the CHAPA metals have a higher reduction potential for water than water. Hence, preferentially, instead of hydrogen gas, these metals get reduced at cathode. Okay, so using this summary, we're going to decide the products of electrolysis. This is writing down once again arrangement of various single electrodes in the increasing order of the standard reduction potentials. So I'm just summarizing what we've just studied. This is H plus. These are group 1, 2, and 13 metals roughly. This is 12, right? These have a lesser standard reduction potential than hydrogen. So in comparison to these, hydrogen gets reduced. But if we compare these, CHAPA metals have a higher reduction potential than hydrogen. So hydrogen gets preferentially reduced, which means if we have a comparison between copper ion and H plus ion, then copper ion will get preferentially reduced at cathode. But if we have a comparison of zinc ion and H plus ion, then H plus ion will preferentially get reduced to liberate hydrogen gas at cathode. This is what we mean by these points. If I write down the order of oxidation potentials, this is the decreasing order of oxidation potentials, where halide ions have a higher oxidation potential than OH negative ion. So halide ions are preferentially oxidized over oxidation of OH negative ion or water. But all these oxo anions have a lesser oxidation potential. So if there's a comparison between any oxo anion and OH negative ion, then it's OH negative ion which is preferentially oxidized. For example, if we have sulfate ion and OH negative ion competing for oxidation at the positive electrode anode, you know, opposite ions attract. Negative ions get attracted towards anode or positive electrode. So out of sulfate and OH negative ion, since OH negative ion has a higher oxidation potential, it gets preferentially oxidized. But if we have a comparison between iodide ion and OH negative ion, if we have a comparison between iodide ion and OH negative ion, then it's iodide ion which has a higher oxidation potential and gets preferentially oxidized. Now, a very important point is comparison of OH negative ion and chloride ion. Now, oxidation potential of OH negative ion is greater than chloride ion, but still chloride ion is preferentially oxidized than OH negative ion. Why? Because the discharge potential of chloride ion is lower than discharge potential of OH negative ion. Now, what is discharge potential? Revising the concept of discharge potential. Discharge potential is the minimum potential at which an ion is discharged. Basically, the minimum potential required, or lower is the discharge potential for an ion, easier it is to liberate an ion at a particular electrode. So if we just summarize and combine all these concepts, what do we conclude? For oxidation at a node, higher is the oxidation potential, lower is the discharge potential. For reduction at cathode, higher should be the reduction potential and lower should be the discharge potential. So an ion which has higher oxidation potential and lower discharge potential is preferentially oxidized at a node. Similarly, the ion with higher reduction potential and lower discharge potential is preferentially reduced at cathode. So if we look at this concept, OH negative ion has a relatively higher oxidation potential than chloride ion. But since it moves slowly, It is kinetically slow because it is highly hydrated. It is surrounded by water molecules. So its overall discharge potential becomes higher. So the discharge potential of chloride ion becomes less than hydroxide ion. Hydroxyl ion has a higher oxidation potential, but more potential than normal is required to discharge it because it runs slowly. Its movement till the electrode is kinetically slow since it's a hydrated ion. So overall जो energy requirement है, overall energy requirement for release of chloride ion becomes less, or in other words we say discharge potential of chloride ion is less than hydroxide ion. So out of chloride ion on OH negative ion, it is chloride ion which is preferentially discharged, and this extra voltage which is required to discharge OH negative ion due to its kinetic factors is called as over voltage. So if I summarize all that we've done, out of all these iodide, bromide, chloride, any of these ions, if we are comparing with OH negative ions, then these ions are preferentially oxidized. But if we are comparing it with oxo anions like sulfate, nitrate, etc., then it is OH negative ion which is preferentially oxidized. Keeping all this in mind, if we just look at some points, these are some important conclusions of NCERT. A negative E naught. E naught means a negative value of standard reduction potential, means that the redox couple, what is the redox couple? Redox couple is, all these are redox couples, metal, iron, metal, or metal, metal, iron. These are all redox couples, H plus hydrogen. These are all redox couples. So oxidized and the reduced forms written together, we call it a redox couple. So if a redox couple has a negative standard reduction potential, means it has a positive oxidation potential, which means it is a stronger reducing agent than hydrogen couple. Similarly, a positive E naught means the redox couple is a weaker reducing agent than H plus hydrogen couple. So this is an important conclusion that you can keep in mind. And another application of this electrochemical series, a metal with a higher negative potential. A metal with a higher negative potential displaces a metal with a lower negative reduction potential or positive potential from aqueous salt solution of that metal. So if I just compare zinc metal with copper metal, zinc has an oxidation potential of plus 0.76 volt and copper has a reduction potential of plus 0.34 volt, or I can say the reduction potential of zinc is minus 0.76 and the oxidation potential of zinc is copper is minus 0.34 volt. So a metal with higher negative potential, displaces a metal with lower negative potential or positive potential from its aqueous salt. Or in other words, we can say oxidation potential of zinc is higher than copper. So zinc gets preferentially oxidized, and since reduction potential of copper is higher, copper gets preferentially reduced. So that's how we decide which metal can displace another from its salt. These are all the applications of electrolysis. So products of electrolysis, looking into quickly into some examples, we have electrolysis of alkaline sodium hydroxide, molten sodium hydroxide. So when we're talking about molten means when we melt sodium hydroxide means we have pure sodium hydroxide, there's no water. So sodium hydroxide ionizes to give these ions. Sodium goes to the positive ion, goes to the negative cathode, undergoes reduction and gets deposited. And at anode, OH negative ion undergoes oxidation to form oxygen gas. Add the two equations, we get this as the overall reaction. No competition, no complication. One ion moves to cathode, another to anode, and they undergo oxidation and reduction. Similarly, if we have electrolysis of sodium chloride, now in case it's a molten sodium chloride, there is no issue. Just one ion, this gets reduced to sodium by gaining electron at cathode, and this moves to anode. Anode is the positive electrode. It loses an electron there and gets liberated as chlorine gas. No competition, no confusion. But if we are talking about aqueous solution. Aqueous means we have sodium chloride ionizing to give these ions, and then we have water, lot of H2O, and very few ions of H plus and OH negative ions, because water is a weak electrolyte. So what comparisons are we going to have? Comparisons are going to be between these two ions to move towards cathode, the negative electrode. And these two ions are going to compete to move towards anode, the positive electrode. So out of sodium ion and H plus ion, we have done standard reduction potential of H plus is greater than that of sodium, all group 1, 2, and 39. So in preference, hydrogen ion will be reduced. Whereas at anode, out of OH negative and chloride ion, we have just now discussed, due to over voltage, OH negative is not able to get released. Instead, chloride gets preferentially oxidized to chlorine. So we get this as the overall change. So for aqueous NaCl, at cathode hydrogen gas, at anode chlorine gas. You have to remember the products. But in case we are talking about a very dilute solution of sodium chloride, since products of electrolysis also depend on concentration, so for very dilute solution, very dilute means it's more of water. So at cathode, hydrogen gas gets liberated, and at anode also water gets oxidized to liberate oxygen gas, because we have more of water in the solution. Electrolysis of copper sulfate, the competing ions and copper ions and H plus ions. Standard reduction potential of copper ion is greater than H plus ion. So it's copper that gets preferentially reduced. And out of oxo anions and OH negative ion, it is OH negative which is preferentially oxidized to give oxygen gas. This is electrolysis of water. Water undergoes oxidation at anode and water undergoes reduction at cathode to give this overall change. Now, this is just a revision. Very quickly looking at the points we have discussed. Fused NaCl means molten NaCl. We have sodium at cathode and chlorine at anode. Fused NaOH, sodium at cathode, oxygen at anode. Aqueous KCl. Aqueous KCl means what are the competition ions? We're going to have potassium ion and H plus ion competing for cathode, and chloride ion and OH negative ion competing for anode. And we just discussed, out of chloride and OH negative ion, it's chlorine which gets liberated, and out of potassium and H plus, that is group 1 metal and H plus, it is hydrogen gas that is preferentially formed. Aqueous potassium sulfate, for same reasons, out of potassium and H plus, hydrogen gas, and out of sulfate and OH negative is oxidized. Aqueous copper chloride, we have comparison between copper ion and H plus ion, where copper is preferentially reduced, and out of chloride and OH negative ion, it is chlorine gas. Then we have aqueous copper sulfate solution. Aqueous copper sulfate, again comparison of copper ion and H plus ion. Copper preferentially liberated. Out of sulfate and OH negative ion, it is oxygen gas from OH negative ion. So this is all about platinum electrodes or non-attackable electrodes. Now we're talking about attackable electrodes. That means if we have aqueous copper sulfate using copper electrodes. So in case we have aqueous copper sulfate using copper electrodes. So what are we going to observe at cathode? At cathode, we're going to have copper ions. We'll have H plus ions, right? So out of these two, it is copper ion which is going to get preferentially reduced. Why? Because the standard reduction potential of copper is higher. So copper gets reduced at cathode. If we compare about anode, for anode we have the anions, sulfate ion, OH negative ion or water, right? And we also have copper of the electrode, which also has a tendency to undergo oxidation to form this, where the standard reduction potential, standard reduction potential of copper is plus 0.34 volt, which means oxidation potential will become minus 0.34 volt. Oxidation potential of this is minus 1.26 volt, roughly 1.23 to 26 volt, and this is some minus 2 point something. So which has the highest oxidation potential? Copper. So at anode, copper of the electrode gets oxidized. So how does this process really happen? We have copper electrodes. Both these are copper. We have anode and cathode. So at cathode, this is copper sulfate. So at cathode, copper ion from here goes here and gets deposited. And at anode, copper of the electrodes goes into solution as copper ion. So aqueous copper sulfate using copper electrodes, we get copper at cathode and copper at anode. But if the electrode instead was platinum, in that case, this option would not have been there. So out of sulfate and OH negative, it would have been water liberating oxygen gas at anode. So whether the electrode is copper or platinum, the product at anode will be different. So hope this helps, children. These are all the possible important questions that can be asked from this chapter. All the best for exam.